So, welcome everybody. We're very happy to have Max Goering here as our speaker today, and we're looking forward to his talk on Finslerian jump regularity theory in Rn. Max, please go ahead.
All right. Thank you for inviting me to give a talk. It's always both exciting and a little nerve-wracking to talk about this because in practice, I'm a geometric measure theorist, and I ended up doing a lot of PDEs and calculus of variations trying to answer a different question. So I'm not by training an expert in this field. So hopefully I can try to make new connections and we can all learn from one another. And hopefully I don't say anything too dumb. So today I will talk about some joint work with Lukas Koch that just got posted to the archive at the beginning of this month. But it'll take us a while to get there. So first, I'll talk about my motivation, which comes from minimal surface theory. And then after maybe explaining why the resulting PDEs turn out to be bad, I'll introduce some new tools for this area that come from convex and Bionic space geometry. And then from these, you can very quickly get a Harnack inequality. So I'll discuss those things. I will not do the entire Moser iteration. In fact, I won't do any of it, don't worry. And then after that, we'll finally get to the new results. And these will be joint work with Lukas Koch. And finally, I'll point out that there's a million unknown questions still in this direction in case anyone finds it interesting. Okay, so what is my motivation? Well, my motivation comes from trying to mimic what DeGiorgi did to study the isotropic or area minimizing surfaces and applying this to what seemed like a naive anisotropic minimal surface that it seemed like everything should be very nice. So to explain this, I'll start by discussing what exactly DeGiorgi did, minus all of the details. So first, we'll consider a set of locally finite perimeter E that's contained in Rn plus 1. And I'll only be concerned with local regularity, so we'll also consider some open set A. And then we'll look at the perimeter of E inside of A, and we'll think of the boundary of E, or the reduced boundary of E as being our minimal surface. So it turns out that if you integrate the Euclidean length of the outward pointing unit normal vector, well, that means you're integrating 1, and this will give you precisely the perimeter of your set. So nothing here should be too surprising, except if you're not familiar, it might seem like a really obnoxious way to write this. But there are reasons. Okay, that's a typo, sorry. So the first thing that DeGiorgi does is shows that you can actually, if you're at a flat point of your minimal surface, you can write the majority of it as a graph. So we're going to just oversimplify and actually assume that our entire minimal surface inside this open set is the graph of some function u. If we do this, then from that area formula, you can rewrite the perimeter now as a functional in terms of u, and it no longer really depends on E in any way. Once you do this, we should all rejoice and be happy and all have the same gut instinct, and that's to compute the Euler-Lagrange equation. And doing so, you get the minimal surface equation. Hopefully, at least this far, things seem semi-familiar or at least believable, but now we'll slow things down because people come from different backgrounds. So the first thing is that in this graphical approximation theorem that DeGiorgi was able to prove, he's actually able to show that your function that is the graph is the Lipschitz function. And because of this, it's kind of natural to consider this matrix A of x. That is the identity matrix divided by the square root of 1 plus the gradient of your function squared. And due to the Lipschitz nature of your function u, this turns out to be a uniformly elliptic matrix. Also, since your gradient's in L infinity, it's a matrix that has L infinity coefficients, and this is precisely why DeGiorgi was looking at elliptic divergence form PDEs with L infinity coefficients when he did his contributions to the DeGiorgi-Nash-Moser theory. But if you look at these two inequalities for a little bit longer, you'll notice that the square root of 1 plus 0 squared is just 1. So if we further assume that the Lipschitz constant of u is very, very, very small, instead of just that it's a Lipschitz function, we assume it's a very small Lipschitz constant, then it turns out that this elliptic matrix is basically the identity. And morally speaking, we now know that near flat points, our minimal surface is primarily the graph of a harmonic function. There are lots of things I just lied about there, but that's the very vague intuition. And because harmonic functions are nice, and we're almost the graph of a harmonic function, we hope that the minimal surface also has nice local regularity properties, at least near flat points. Okay, so now formally we're going to assume that there are no problems with this same setup, and we're going to try to do it again for a nice anisotropic problem. So the anisotropic energy that I want to consider is the exact same situation as last time, except now, instead of considering the Euclidean length, we'll consider the LP length. And just so that we're all happy, we'll make sure that p is bigger than or equal to 2, so everything's twice differentiable and we'll never have to worry about whether or not we can actually compute derivatives. If we once again make the simplifying assumption that our minimal surface is the graph of a function, we can once again then ignore the minimal surface itself, and we can write this as a function, or as a functional of u. So we'll once again do what comes natural to us and compute the Euler-Lagrange equation. Unfortunately, now when we compute the Euler-Lagrange equation, we don't get something that looks as nice as before. We get this thing that I'm going to call, for hopefully obvious reasons, the LP minimal surface equation. Due to what we did last time, we decide that we should, for the sake of simplicity, assume u is not just a Lipschitz function, but as a very small Lipschitz constant. And we'll define this matrix A of x, that's the identity divided by the LP norm of our gradient, comma 1, raised to the appropriate power. Then, once again, this matrix is elliptic, has L infinity coefficients, and once again, when the Lipschitz constant is close to 0, we get that this matrix is approximately the identity. So doing the same linearization process in the small gradient regime that DeGiorgi did, we learned that near flat points, anisotropic LP energy minimizing surfaces solve this equation, almost solve this equation, which we're delighted to know is something someone before me has studied. If I was the first person to look at this, this would maybe seem very contrived, but this has been studied before and other people find it interesting as well. And it's actually called the Pseudopilloplastion. And so in weak form, you can write this differential equation this way. And it's perhaps the prime example, it's definitely the best studied example of Finslerian, which will be the broad class of PDEs that I want to talk about in general today. I guess you could say the Laplacian is probably the most studied one, but that's too studied. It's not very interesting these days. And the P-Laplacian is also very well studied, but it already has the regularity properties I want. I'd like to say that these functions are C1 alpha, because we assumed they're Lipschitz from the beginning. So we'd like to improve their regularity. We'd like to improve the Lipschitz regularity up to C1 alpha regularity, and use this to recover higher regularity for our minimal surfaces. Unfortunately, even for the Pseudopilloplastion, this is not known. Just for those of you who are interested, calculus of variations comes into play precisely because, just like in the area minimizing case, this is the Euler-Lagrange equation of some functional that's easy to write down and understand. And so this brings us to our question, which we can ask in a couple ways. What's the regularity of minimizers of this type of functional, where rho of x is some family of norms, and gamma is any positive power? It turns out that when you take the Euler-Lagrange equation of corresponding to that functional, you get what I call the equation 1 here, and that is the general form of the Finsler, now gamma Laplacian. I perhaps did an annoying thing, and I decided to call this the Finsler gamma Laplacian because I wanted P to be preserved for the LP norm. So anytime I say like a gamma Laplacian, you can think P Laplacian, but then if you do that, just remember that there's a different P that might mean something else floating around in the rest of this story. Okay, so what is known, or wait, where do I go next? Let me look ahead, perfect. Let's look at some examples of Pseudopilloplastions before we get ahead of ourselves. The kind of obvious ones that I've already mentioned are the Laplacian, the Pseudopilloplastion, and the Pseudopilloplastion. These first two, you take your family of norms rho of x to be identically the Euclidean length. For the Laplacian, you choose gamma equal to 2. For the Pseudopilloplastion, you choose gamma equal to p. For the Pseudopilloplastion, you take your family of norms identically equal to the little LP norm, and then you choose gamma equal to p. In both of these cases, and that's how you reduce this general class of equations to ones that are maybe more tangible. You can also recover many other equations. For instance, if you let your family, this is a typo, let your family of norms, rho of x, depend on xc, and then this should be xc and this should be xc, there we go. And then if you choose this norm, you recover all elliptic divergence form PDEs with symmetric L infinity coefficients. The only reason you need symmetry is that this sort of inner product doesn't see the anti-symmetric part of your matrix. And then finally, the other things that actually already came up in our motivation is you can cook up this matrix A of x in different ways so that you recover the minimal surface equation or the LP minimal surface equation. And so by studying the whole class of the Finsler gamma harmonic functions, we have hope of improving the regularity of LP minimal surfaces or other anisotropic minimal surfaces. So what's wrong with the Pseudopilloplastion? First of all, it's very degenerate. The best known regularity in Euclidean space is that the solutions are Lipschitz regular. This was proved by Demangel in 2017. And later for the orthotropic Pseudopilloplastion, with the appropriate bounds on your different powers, Lipschitz regularity was also shown. So the orthotropic Pseudopilloplastion is a slight variant on this thing, where you let your power p vary for each of your partial derivatives u. I've been told that I should not call this first equation the Pseudopilloplastion and that people don't take that very seriously, but I think it's more important to be clear in my language. So the one where all of the pi's are the same will always be called the Pseudopilloplastion when I'm talking at least, and the one where they're allowed to vary will be called the orthotropic Pseudopilloplastion. So both of these cases, as long as your pi don't vary too much, are known to have Lipschitz regularity for solutions in all dimensional Euclidean spaces. And in fact, in the plane, Brosco and Bousquet showed in a very lengthy 274-page paper that solutions are C1. I hope this isn't the only thing they proved. I haven't read the whole thing, shocker, I know. But in the same year, C1 log regularity was shown by Lindquist and Riccati in a 9-page paper. So they both got, so I assume the original paper had other ideas in it, but Lindquist and Riccati, although they're published in the same year, definitely give a lot of credit to the original paper by Brosco and Bousquet for their work. So. And I already mentioned the orthotropic Pseudopilloplastion once, but there's been a lot of work done by a lot of people where they've taken other variants of the Pseudopilloplastion. Sometimes they add degeneracies near the origin and so on, and they get similar results to some of the ones that I recovered with Lucas Koch, and in other scenarios they get Lipschitz regularity as well. So the degeneracy is bad enough for the Pseudopilloplastion that these are currently the best known results, and none of them are known to be sharp. There are, as far as I know, very few solutions that anyone can write down for the Pseudopilloplastion. I can write down 2. There's the fundamental solution, and then one other that comes from assuming you're a sum of your function that depends on each direction independently, the sum of those things. So if you assume your solutions of the form u of x is the sum of fi of x times fi of x dot ei, for some functions fi, and then start making simplifying assumptions on the form of fi, you quickly stumble into one other solution besides the fundamental solution. Both of these classes of solutions are C1 alpha for some alpha, for all dimensions, and for all p. It's unclear whether this is what you should expect for the full regularity of the Pseudopilloplastion. I think it's a little bit better than what you should expect, but hopefully you can still get to an alpha with just a smaller alpha. Very unclear. If anyone's good at coming up with counterexamples, aim in this direction and I'd be very happy. Okay, so why is it so hard to get regularity for the Pseudopilloplastion? Well, if you take the Hessian of the LP norm and you plug in any of your standard basis directions, you get the zero matrix. In particular, if you take the Hessian of the LP norm raised to the power of p, this has to be some rank 1 matrix. No matter what dimension you're in. So when we remember that the Pseudopilloplastion comes as the Euler-Lagrange equation of this functional, and this functional has Hessian that is rank 1 in Rn, we begin to realize that there can be a lot of information that's being hidden by the second order behavior of our PDE. And so this makes it very hard to recover really any information about how the solutions behave. One more example that I want to emphasize for the Pseudopilloplastion, and I guess this one points out why the Finsler gamma Laplacian is even more challenging, is that if all you do is rotate the LP norm, so let's assume that A is some orthogonal matrix, and you define your norm to be this rotation of the LP norm, then this expression that I've written down in this green box is what your Finsler gamma Laplacian, Finsler P Laplacian looks like with respect to this norm. However, when P is not equal to 2, because of this term in absolute values, you have a complete mixing together of all of your derivatives. They're inside an absolute value. You have no linearity and you have no hope of being able to solve for each of your partial derivatives individually in terms of your other partial derivatives. And this sort of algebraic manipulation is the key to the majority of the techniques used in the study of the orthotropic P Laplacian. The techniques that have been used for the model case are in general not helpful at all for studying the Finsler gamma Laplacian. And this is why we need new techniques. So a refresher or reminder, our question is, what's the regularity of weak solutions of the Finsler gamma Laplacian? And we just realized that none of the known techniques are going to help us very well. So what can we do? Well, what I've been able to take advantage of so far is some duality techniques that are actually well known and used all the time in Banach space geometry and convex geometry. I called them new tools. Oh, come back. With new definitely in quotation marks, not only because they are from other fields and I didn't invent them, but also because they've been used a lot in the calculus of variations. However, in all of, I'm sure this isn't an exhaustive list either, this is just what I'm aware of. Remember, I'm not an expert, so if I've forgotten your paper, please don't be offended. But in at least all of these papers, authors are still working in some uniformly elliptic setting. And so the fact that they're using these duality methods is kind of hidden, or is just something that they use at one point and then completely forget about when they could have kept taking advantage of it. And people didn't seem to realize that this is a recurring technique that they can use a lot. They've also been used in PDEs by at least these people, and besides Ferrone and Cavall, none of the other two papers were again assuming uniform ellipticity. So the things I said before about things being rotationally invariant enough still kind of applied to their work. So we'll want to take advantage of these duality techniques. And to do this, we'll want to better understand some of these tools that are known by other fields. One of the more important things for the work that I've done that has come from this is not just a duality mapping that I'll define once we've learned enough other words, but they also have quantified notions of convexity of a Banach space and quantified notions of smoothness of a Banach space. So given some Banach space x comma rho, or rho's the norm on the Banach space, we can consider the modulus of convexity defined in this way. I wouldn't be too worried about the precise definition. The intuition you should have is that the modulus of convexity tells you that if you look at a scale epsilon of some tangent plane to the unit ball, that the unit ball in this Banach space has to curve away from the tangent plane and at a certain rate that's quantified by this modulus of convexity. So the modulus of convexity tells you you're not too close to a tangent plane at a large enough scale. And then on the exact opposite side of things, you have a modulus of smoothness that tells you when you're looking at small enough scales, your unit ball is already close enough to its tangent plane. And so again, let's not worry too much about the definitions, but those are the two intuitive ways that I think about them. And I would suggest that you do too, at least for this talk. And so far, these are just functions you define for some Banach space and some norm. But we want to now look at a class of norms that have quantified convexity and quantified smoothness. So if you pardon a slight abuse of notation, we say that a norm is sigma convex if its modulus of convexity at scale epsilon is at least as big as epsilon to the sigma. So this sigma and that sigma, totally different things, but the one on the left won't show up again after this slide. Also, we say that a Banach space is tau smooth if its modulus of smoothness is less than or equal to the scale you're looking at raised to the power of tau. And so these things together say that if you're sigma convex, your unit ball separates from tangent planes at least as fast as x to the sigma, or your scale to the sigma. And the smoothness tells you that you're squished between parabolas like your scale to the tau when you're looking at just that scale epsilon. All right. And one key property that starts to introduce the duality going on here for the smoothness and convexity is that if you have a sigma convex and tau smooth Banach space, then the dual Banach space is sigma prime smooth and tau prime convex. This will always be the case, and this is because of the duality between smoothness and convexity. So some examples of some Banach spaces that we've all seen before is the little LP and the big LP spaces. When P is bigger than or equal to 2, these spaces are 2 smooth and P convex. And when P is less than or equal to 2, they're P smooth and 2 convex. And notice again that these two things kind of have that's not supposed to still be a highlighter. These two things still have that duality relation going on that we talked about up here. But here's where things maybe get a little uncomfortable, at least if you learned about Sobolev spaces the same way I did. So when I learned about Sobolev spaces, I was told it doesn't matter what norm you put on them, just take all of your different multi-indices, sum over all of them, take the maximum over all of them, it doesn't matter, do one of these things and you'll get a Banach space, and that space is called the Sobolev space. But if you say put the little LQ norm on the different components of your partial derivatives of your function to define your W1P norm, this changes the convexity and smoothness of your Sobolev space because we're changing the norm. And so, for instance, when Q is equal to 2, it turns out that this Sobolev space will have the same smoothness and convexity as the LP space is. When Q is equal to P, I think, although I haven't actually taken the time to prove this, I think that, once again, the Sobolev space will have the same convexity and smoothness as the LP space is. But when Q is equal to 1, that's not the case. And so it's unclear to me what happens in general for different values of Q, but you do actually have to be careful with how you define your norms in order to talk about the smooth structure. And this became very relevant in the work with Lukas Koch, because the work that we did ends up not only working for systems, but it works for Banach space valued solutions to a weak PDE. And so you have to be aware of how to relate the norm on your Banach space to the different components of your directional derivative, because your gradients, in some sense, will live on the space. You'll have your Banach space tensor product Rn. And you need to define some norm on that space that should reasonably depend upon your norm x. And what we were able to show is that if you do the analog to what we did here, but with Q equal to 2, you don't make your convexity or smoothness worse. And so we were happy with that and called that the natural thing, because you take the norm from R You take the natural norm from Rn, and it turns out to work out all right for not only our proofs, but also for your intuition. All right, so we've quantified everything, maybe too much, sorry about that. But now we're ready to finally define the duality pairing. So given some reflexive Banach space, X rho, we can define the duality mapping, I'll call it capital J very briefly, rho gamma of X. And this is the set of points in the dual space such that the dual norm of the points has the same norm as X itself, just raised to the power gamma minus 1. And when you do the duality pairing in your Banach space of this point X with X itself, you recover the norm rho of X raised to the power of gamma. This looks kind of annoying, but it turns out that both of those identity are themselves very useful. And I had originally thought they were a consequence of, because this is a reflexive Banach space, you have this specific representation of the duality mapping, which was the first thing I saw, and I only later learned about the more general definition. It turns out that the specific representation is pretty useful, but let's look at some other nice properties. It turns out that if you have a uniformly smooth Banach space, so what that means is that our modulus of smoothness, if we look at tau x epsilon over epsilon, and let epsilon go to 0, this has to approach 0. If that happens, you say you're uniformly smooth. And this just says that at some fixed rate at every point, you're going faster you go to 0 faster than linear when you're approaching your tangent planes for the unit ball. This property tells you that this dual mapping is actually single valued, which is very important for defining a PDE in terms of these things. And also you learn that it's locally uniformly continuous. But you learn a lot more. We know that the dual space is uniformly convex, and this is once again the duality between convexity and smoothness appearing. We learned that the Banach space is reflexive from the uniform smoothness. That's what allows us to use the representation that I have in the first line. We learned that from uniform smoothness, our duality mapping is surjective. And now I started writing the duality mapping with the lowercase j. This isn't my convention, but you use the lowercase j only after you know it's single valued. So now that we know it's single valued, we can quit writing capital J's. And we know that it has an inverse. And not only does it have an inverse, it has an inverse that we know how to write down. So the inverse of our dual mapping from x to x star happens to be the dual mapping from x star to x, when instead of using the power gamma, you use the power gamma prime, where gamma prime is the Holder conjugate to gamma. And this is extremely useful in manipulating expressions in order to get out the types of inequalities you want. And I think I already said this one because I started using lowercase j's, but great. Oh, I see. The uniform convexity of the dual space tells you the primal space has single valued duality mapping, and therefore this thing is single valued, so it's a true inverse. Because it's a true functional inverse, we then learn that these things are also homeomorphisms, not only that it has an inverse. So we now have a homeomorphism between our two Banach spaces with an inverse that we know how to write down. And those are all of the tools that make things work. And it turns out you can, I think, simplify a lot of the proofs that already exist in the literature using these tools. So where have we all seen this duality mapping before? Well, unless you showed up late, you all saw it at the beginning of my talk, because you can write down the Finsler gamma Laplacian as just being the integral of your duality mapping of your gradient paired in your dual space, or in your Banach space. So we could write this way, maybe to be a little more consistent, but that's more tedious, so I won't keep doing that. You can look at your Finsler gamma Laplacian this way. Also, if you do know minimal surfaces, and you are aware of the tilt excess, this is the measure of flatness that DeGiorgi used for his Lipschitz approximation theorem. And it just so happens that it can be written down in terms of the duality mappings of the outward pointing unit normal vector to your minimal surface and the direction with respect to which you're flat. So it's reassuring that these things have shown up before. And this latter one, the integrand of the tilde excess, is sometimes called the symmetrized Bregman divergence between the two vectors. Okay, and so now we're more than prepared to prove our first theorem. We only have to prove one theorem in a talk. So after that, you can go cook, I think is what I heard. So we'll prove Kachopoly's inequality. So if you fix some family of norms rho sub x, for each fixed x, your norm is uniformly smooth, and for each fixed x, your norm is uniformly convex, and you have some gamma between 1 and infinity, then any subsolution of the Finsler gamma Laplacian with respect to this family of norms satisfies the Kachopoly inequality. I'm not actually going to prove the whole thing. I'll just give you the idea. Step 1 is to choose the correct test function and plug that in. Step 2 is that if you aren't super familiar with the proof, open up your favorite PDE's book and look at the usual proof for divergence form equations. And from there, we recall the two properties that are used to define the duality mapping. Because we can keep track of the homogeneity of the expressions that will show up when you plug phi in as your test function, you're able to apply Finchel's inequality in lieu of Holder's inequality, which tells you that this dual pairing will behave exactly the way you want to replace upper ellipticity. So this inequality replaces upper ellipticity. But it's this equality that replaces lower ellipticity. And so now, by replacing those two things appropriately, in say Han and Lin, then you'll be able to mimic the proof exactly, you'll have less constants floating around, and you'll recover the Kachopoly inequality. And that's kind of the idea, maybe, of looking at these Finsler gamma Laplacians, is to, if you look at things in the correct norm, it makes the proof simpler. Maybe that's a consequence, not an idea, unclear, but I've enjoyed this realization. So in 2020, I put a paper on the archive that could be summarized as the Georgi-Nash-Moser does not need ellipticity. In short, this means that if you perform Moser iteration on the Finsler gamma Laplacian, everything converges, and therefore you attain Holder continuity of solutions, a soup bound, an inf bound, strong maximum principle, a Harnack inequality. Those are all of the classical things, I think. Oh, and a Liouville theorem. And when you look at the specific norm that I chose, family of norms rho sub x of c to be the identity divided by negative du1 LP to the p minus 1, you can now apply the Liouville theorem back to our LP minimal surface equation and find out that if global minimal surfaces that are graphs over the standard basis Euclidean plane are bounded above or below, then they're a plane. And so this is the first improved regularity result I've been able to achieve. It's a statement only about the tangent minimal surfaces, more or less, but it's the only part I've been able to apply yet to the theory of minimal surfaces. So it was nice to at least get a first result in there. The rest of this, though, was maybe a little sad because I was born too late.
Can I just, maybe I missed something. Can I just ask a quick question? So go back to the Bernstein theorem. So,
yes.
So, I mean, is there a dimension restriction on the domain?
There's no dimension restriction because we're assuming graphicality. So a Bernstein theorem is false in general for area minimizers, but if you're looking at area minimizers that are the graph of a function, then a Bernstein theorem holds.
Right, okay.
Any other questions? I've forgotten to ask that this entire time, I think. All right. So the only downside to this result is that these parts were already known in 1984 because Giacinta and Giusti showed that the Georgi-Nash-Moser doesn't need ellipticity. They approached it from a calculus of variations perspective instead of a PDE perspective, and they used the Georgi's approach to the Georgi-Nash-Moser instead of Moser iteration, but they got all of these things for almost the identical setting that I was able to do. But I still wanted to mention these results because I've been talking about these results for almost 2 years, and only within the last month has anyone pointed out to me that most of them were already known. So I think that it's not very well known that you don't need ellipticity to do Georgi-Nash-Moser. Maybe it's well known if you talk to the right people, and I've just been talking to the wrong people, but it's not known well enough. So all right. So now let's look back to, well, I guess the good news is that's not all that I know about the Finslerian Laplacian. I've been able to do other things. Still not as much as I'd like, but we're making progress. So if we go back to our quantified notions of convexity and of smoothness, then due to some work of Zhu and Roach in 1989, there are nice inequalities that you can use to characterize the convexity of a Bionic space. And what this says is that if you look, and what their characterization says is that a Bionic space is sigma convex if and only if the difference of dual vectors paired with the primal vectors is bounded below by, so this first piece, all that you should think about here is that it's something that preserves the homogeneity. And then the second piece is something that looks at the distance between the two primal points. So we can now relate the pairing between dual and primal vectors. We can understand them by just looking at the difference of the primal points and also keeping track of homogeneity. They also show, and this should maybe be no surprise, that you have a similar inequality for the smoothness of a Bionic space. And this follows from the fact that everything happens through duality. And so it turns out that if you look at the difference of two dual vectors, and then you apply the dual norm to that difference of vectors, this is bounded above by something that preserves the homogeneity, and then something that tells you how far apart your two primal vectors were. And these inequalities turn out to be very exciting if you've ever done any proof by difference quotient methods to show regularity of a function. You can look at these things and say, hey, I bet I know what we can do here. Let's try to look at the discrete differences of our solutions and see what this tells us about the regularity of our solution. And that's exactly what I've done with Lucas-Koch. But maybe to put this in a little bit better perspective, let's discuss some previous work. So at least as far back as Uhlenbeck's work in 1977 on harmonic maps between manifolds, and later in a much simpler setting with a simpler proof by Boyarsky and Bionic, it was shown that for p-harmonic functions, if p is bigger than 2, and you define this function f of x to be the size of your gradient raised to the power p minus 2, multiplied by the gradient itself, then this function happens to be in W1 too. So this weird nonlinear function of your gradient turns out to be a Sobolev function. And this tells you, at least to some degree, that your original function has more derivatives than you had, or more weak derivatives than you had thought it would, because at least away from the origin, this and infinity, this first part behaves nicely. And so when you do the product rule, the second part has to have another derivative as well. So how do Boyarsky and Bionic do it? Well, their proof boils down to difference quotient methods combined with these two elementary inequalities. And those elementary inequalities don't look very fun, but I also think a lot of you in the audience have probably proved similar inequalities in the appendices of your papers. And they look to me like the characteristic inequalities that were proved by Zhu and Roach for Bionic spaces. Unfortunately, they're not exactly the same, but let's pull those two things up side by side. So the characterization of sigma convexity, we have this difference of dual vectors paired with the difference of primal vectors. If we were to assume that rho is the absolute value, and gamma is equal to p, then the right-hand side of our sigma convexity says exactly that x to the p minus 2x minus y to the p minus 2y, we want to take the inner product of that with x minus y. And now we realize that's exactly the right-hand side of this first inequality from Boyarsky and Iwaniak. Unfortunately, the left-hand side does not match up as well. In their work, they have this lovely power of 2, and I have this very unfortunate sigma, because it turns out that sigma has to be bigger than or equal to 2, and when it comes to the smoothness, tau has to be less than or equal to 2. So in the case where sigma equals tau and they both equal 2, which is the case that you're in for the Euclidean norm, these inequalities look a lot more alike than they do otherwise, and you get a closed loop that you can iterate a lot easier than you do in the general case. As for the tau smoothness inequality, you can maybe convince yourself that the dual of Rn is Rn with the Euclidean norm still. And so the left-hand side of their second inequality is exactly the left-hand side of the tau smoothness inequality. And then this time it's the right-hand side that's a little inconvenient for our purposes. But nonetheless, with Lucas-Koch, we're able to show that if you have a sigma convex tau smooth norm, and you have some gamma that's bigger than 1, and you have a solution to the Finsler gamma Laplacian, then, and things get worse than in the original case, I do apologize, then we get fractional derivatives. So before I introduce fractional the notation, let me define things real quick. So I'm going to say the space B alpha P log infinity. It's a lot of ways of decorating a space. It wasn't my choice. This should be the real interpolation between LP and W1P. And that is hopefully meaningless to most people. It certainly was to me. That's too much functional analysis. So instead, we'll say that we can characterize this for Banach spaces that have the Radon-Nikodym property. Okay, that might also be scary, but all reflexive Banach spaces have that, so we're happy again. So in these reasonable Banach spaces, this is equivalent to saying that you can take the integral of u at x plus h minus u of x over h to the alpha, and raise all of this to the power of p, and this is over some compact subset of your domain, and this is less than some constant. In the case where alpha equals 1, this is exactly the difference quotient characterization of W1P. But here we just have it for some alpha between 0 and 1, and so this still is in some way telling us we have a fractional derivative of our solution, if we're in B alpha decorated appropriately. Okay, so now we're going to see a lot of these Sobolev spaces at once. So the first things are that if you solve this, as I have been saying, then your dual vector to your gradient, or your dual gradient, has alpha 1 fractional derivatives, where alpha 1 is the minimum of your smoothness and your homogeneity minus 1. So we remember that gamma is bigger than 1, and tau is between 1 and 2. So we have at least some extra differentiability for our dual vector. In the nice case where tau is 2 and gamma is at least 2, we get that the dual vector is in some Sobolev space for all of these, or for all of these PDEs. If we want to look at our actual gradient itself and not the dual gradient, then you find out that you have whatever your regularity was for the dual gradient. So I wrote this as alpha 1, but that alpha 1 that shows up there is precisely the differentiability of the previous dual function. So if you magically know that alpha 1's bigger, you get better differentiability here as well. So here you learn that you get alpha 1 plus 1, so just the minimum of your homogeneity and your smoothness, now divided by the maximum of your homogeneity and your convexity. So this will once again be between 0 and 1, but this time in order for it to be 1, so this equals 1 if and only if sigma equals gamma equals tau equals 2. And if all of those things equal 2, then you're exactly in the divergence form elliptic PDE setting. And so we recovered DeGiorgi's W22 result. But now is where we get to play with nonlinear quantities of our gradient. And we were thankfully motivated by the inequalities in lots of papers, but also the Bionic paper. And we're able to show that if you take the gamma minus sigma over sigma norm of your gradient, multiplied by your gradient, so you should think of this as being du to the p minus 2 over 2 du, or at least compare it with that, then this will have alpha 3 fractional derivatives, where alpha 3 is just the differentiability of your dual of your gradient plus 1, now divided by your convexity. Since the LP norms have convexity, for p less than 2, have convexity 2 for all p, then, never mind. What I was gonna say is simpler for the next one, so I'll just wait one line before I say anything. And then here we have basically a dual version of the same equality, where now we have our dual of our gradient multiplied by some appropriate norm. Remember that the smoothness of the dual Bionic space, or the convexity of the dual Bionic space, is tau prime. So this tau prime shows up literally because it's the dual convexity. So these two expressions look almost identical, but we find out that this dual vector has alpha 4 fractional derivatives, whatever that means, where alpha 4 is a minimum of our homogeneity and our smoothness, but now divided by tau prime. In particular, alpha 4 is completely independent of the convexity of your norm, which I found very surprising. But I found that surprising because the convexity is like what plays the role of lower ellipticity in everything I've done. So I was surprised that independent of your lower ellipticity, we were still able to get the same amount of differentiability. In some intuitive sense, that's probably a lie, but that's hopefully a helpful way to think about it. Nonetheless, this is what happened. And also everything we did holds for systems. They can be Rn valued functions, and they can also be Bionic space valued functions. Not gonna fully explain what we did here, but think back to the example I had in red about Sobolev spaces, and that's kind of how we defined the norm on the space of gradients, which I didn't say any words about that, so okay. But I agree with, I assume all of you, that this alpha 1, alpha 2, alpha 3, and alpha 4 looks pretty annoying. So let's try to just compare to things that are already known, instead of try to understand what they all mean, because to understand what it means, it's probably better to just pick an equation you care about and then figure out what it means in that case. So if you compare what we've done to the work of Uhlenbeck, Boyarsky, and Iwaniak, you recover their results which hold for p greater than or equal to 2, though they didn't hold for p less than or equal to 2. You can compare those to this equation that we have at the bottom that says this function has, it turns out in that case, exactly 1 fractional derivative. Why do we get exactly 1? Because the smoothness, or because the Euclidean norm is too smooth, and because our homogeneity is bigger than 2. So this minimum is exactly 2. 2 minus 1 plus 1 is 2. So this becomes a 2. And 2 prime is also 2. So 2 divided by 2 is 1. So we get a full derivative for the P-Laplacian. The same thing holds true for the Pseudopilloplastion. This was a result already known by Brasco, Leone, Pesante, and Verde, and there's similar results known by Brasco, Carli, and Sant'Ambrogio, where they add other degeneracies near the origin. And we're able to recover, except for this one. So this one has extra degeneracy. But except for this one, all of the equations that actually arise as the Finsler gamma Laplacian, we've recovered the sharp results that were previously known in the literature, while also covering a lot more equations than specific orthotropic ones. So I was pleased with being able to recover so many results in one go. Besides doing difference quotient methods and using these characteristic inequalities, I've probably said the words dealing with the nonlinearity of the gradient, and without saying too much, we needed some analog of V function inequalities to do this, and we showed in our paper this sort of comparability, whatever that means, and this might be of independent interest to allow people to look at their specific equations. But this is what allowed us to take these results and in some sense interpolate between them, and you magically come up with these as the sharp or best functions that are somehow fall between those two things that have the most differentiability. So are there any open questions? You betcha. There are lots of them. The first one is Lipschitz regularity true for the Finsler gamma Laplacian? For my motivation, I'm assuming that my graphical approximations are Lipschitz. I get this for free for other reasons. So it'd be really problematic if the actual function that I'm saying it's close to isn't Lipschitz regular. So it'd be lovely to know if that's true. It's only known for the pseudo-P and orthotropic P Laplacians. Another question might be if W2 gamma regularity is known. I think that for certain Finsler P or gamma Laplacians, it's easy to disprove this, but in general, I don't know. But I think you can disprove that by looking at the fundamental solutions. Is C1 alpha regularity known? This certainly shouldn't hold for all of them, but can you quantify the convexity and the smoothness in some nice way to get classical higher order regularity? And one nice thing about C1 alpha regularity is, unlike with the weak derivatives that we have in my result with Lucas-Koch, for classical derivatives, if we know that the dual gradient is smooth, then you're going to know the original gradient is smooth everywhere except the origin. Because we have this homeomorphism, and the homeomorphism is uniformly continuous. So, and usually better than that. And so you're able to recover the regularity of one from the regularity of the other, and this raises the question, or this raises the possibility of showing that maybe you don't directly show your gradient is smooth, but you show some weird dual function is smooth, and as a consequence, you learn your gradient is smooth. This is what we were hoping for, but we weren't able to get high enough regularity to do that. I see I didn't save all my pauses. I might go this way. So then the following question is, are there counterexamples? For bad enough norms, that's the only one that I know of counterexamples for. Can you also, I mentioned this extra degeneracy added by Brasco, Carlier, and Sant'Ambrogio for their results similar to ours. I would assume that you can also adapt a combination of their techniques and ours to get these sort of Sobolev or Besov space regularity results for Finsler P Laplacian type equations with a cutoff function near the origin. You could also ask if there are non-local analogs of these regularity results for a non-local version of the Finsler P Laplacian. And since one of the few things that we know about these things are that they have a fundamental solution, they're not linear equations, so it's not super useful on its own. But this is the fundamental solution, and this raises questions for people who are trained in geometric measure theory, at least, of whether or not you can characterize or imply rectifiability from the existence of principal values or the L2 boundedness of singular integral operators, thanks to knowing that things should be written down with respect to these specific fundamental solutions. This would be like an anisotropic version of the T of 1 theorem or the Mattila-Price theorem. And there's also questions about just whether you can do the price density theorem with any ball that's not the Euclidean ball. None of these things are known. I think this last one is very far outside of things that people can approach right now. But at least the qualitative one, so rectifiability with existence of principal values, I've been working on that with Tatiana Toro and Bobby Wilson, and for nice enough norms, we've made progress. And we think that there's hope to do other nice enough norms. We just don't know what that means yet. So there's hope to apply these same techniques to more classical questions in geometric measure theory, as well as, I'm sure, lots of anisotropic questions in geometry. So thank you.
Yeah, Max, thank you very much for this very interesting talk. And so let me now ask whether there are any questions.